now we'll start with the electrical layer, which has various subcomponents. So largely, you see a transmitter on the left and the receiver on the right. And within each transmitter and receiver, there's a part called data path, which take the data from the core and then drive through the channel using the driver. And there's also another part called clock path, which will generate clock necessary to trigger these circuits inside the data path. Yeah, this is basically what I just mentioned. Let's start with the clock path. So first part of the clock path is the circuit that generates a set of clocks. And we need multiple clocks that we have to propagate to the data path. Some of them will drive the driver for the data. Some others will drive the driver for the valid. And last one is the driver for the clock. Okay. And the reason we use different clocks for each of those is because we want to adjust skew between them. That becomes important when we talk about logical layer. But they all come from the same source, which is generated by a series of phase lock loop, duty cycle corrector, and a delay lock loop. So first, the phase lock loop will take a 2 gigahertz input clock and multiply the frequency. And here, the multiplication factor n is determined by the data rate that you want to operate at. Earlier I said UCIe has to support multiple data rates. So that data rate will basically choose this n. And the resulting clock will have a higher frequency, but there's no guarantee that it will have a 50% duty cycle. So we'll have a duty cycle corrector that maintains duty cycle at 50%. Now, the next stage, we have a delay lock loop, and this one is used to generate a set of multi-phase clocks, like set of clocks that span 360-degree phase in uniform steps, because this is used for the next stage phase interpolators to generate a digitally adjustable clock phases. Okay, so we'll first go through each of these components and see how we can model them in SystemVerilog using the XMODEL primitive. So the first one is a phase lock loop. As I said, this is basically a feedback loop that's made of a component called phase frequency detector, charge pump filter, VCO, and a frequency divider to take a 2 gigahertz input clock and produces an output clock ranging from 2 to 16 gigahertz, depending on the dividing factor, for this frequency divider. So this is actually a that's been visited by multiple people. There's a lot of material out there. We also have demo, tutorial, and video. So we're not going to go too much detail into that. But two unique requirements when it comes to UCIe is that first, this PLL has to support multiple multiplication factors to support the multiple data rates. And for all those output frequency, we like to maintain a constant bandwidth. Why? Because we have the fixed reference frequency coming in. And the other requirements, we would like this PLL to have a lock detector because this is one signal that the logical layer requires. So we'll basically, it will let the PLL to start, and it has to wait until the PLL says, oh, I'm locked. And we need a lock detector says, I'm done, move on to the next step. Well, as I said, I'm not going to go too much detail into each of the blocks of the PLL because, again, this is a well-visited topic. And also, the other components like DLL, DCC, they use the similar components anyway. So we're going to visit some of that already. But if you want to know more, here is a link to the video, YouTube video you can watch. And well, the PLL actually serves as a really nice example to learn different types of the XMODEL primitives because let's say the PFD, the phase frequency detector, is mainly a digital circuits, but you extremely care about the timing. So you can use the XMODEL's logic gate primitives for that. For the second block called charge pump, it's basically a set of switchable current sources driving a resistor and capacitor. So it's a natural fit to a circuit primitives. VCO, it generates clock as a function of its whose frequency changes as a function of the input voltage. So here we are taking the input, converting to a frequency, and then generate a clock from that frequency. So it's a natural candidate for a variable domain translator, which can do the conversion between the frequency and clock. And then lastly, the frequency divider. Typically, you want this to be programmable, maybe even synthesizable in that regard. So you will describe it in pure Verilog. And all of that can be done within the SystemVerilog using the XMODEL primitives. So for the requirement on maintaining constant bandwidth, here are the expression for the natural frequency and the damping factor zeta. I'm not going to describe the derivation process, but the point here is that the natural frequency is a function of the charge pump current, VCO gain, the dividing factor, and the loop capacitor. And among them, the N factor is going to change. So to keep this bandwidth constant, we have to scale either the charge pump current or the VCO gain proportional to the N. Both are possible, but in this webinar, we'll show how to scale the VCO gain because we actually scale current for the other examples. So just for the diversity. So here's the model for the VCO that will scale the VCO gain as a function of the multiplication factor N. Basically, it describes a VCO whose frequency is a linear function of the control voltage. So to do that, we take the input, we subtract with the center voltage. Okay, so this is what's called add primitive, which can also perform subtraction by giving a negative weight, and then you scale it with the VCO gain, whose gain is actually determined by some inline primitive as a function of the control code. And that will determine the frequency value. And we use this primitive called frequency to clock primitive to generate a clock with that frequency. Okay, so this is how you can construct the analog model by putting these XMODEL primitives. So the divider, as I said, is going to be programmable based on the data rate they want to operate at. So in this example, we're using 4-bit codes to set the dividing rate. So the first part will decode that code into the actual dividing factor. And the second part is the Verilog description describing the programmable frequent divider. One thing that stands out here is that it does have a retiming flip-flop, because when you describe your divider in pure Verilog, it is subject to the quantization effect due to the fixed time step of Verilog. So what we do is we take the output of this Verilog-based divider, retime it, we resample it with the input clock, which has the X bit type, which can have a precise timing regardless of the Verilog time step. That way, the output clock can be synchronized to the input clock without suffering the quantization effects. That's one trick. For the PLL lock detector, well, this is mainly a behavioral model, maybe too abstract, not directly correspond to some circuit implementation. For the sake of simplicity, we describe it as a logic that monitors the frequency and phase of the feedback clock for a while, and it will assert the lock signal when those values are within the 5% of the desired the final value for 128 cycles. So if it reaches the final point and stays there for enough period of time, we say it had reached lock. Okay, so let me just briefly flash you what it would be like to run this model in the Glister environment, which is based on Cadence Virtuoso. So here's the command interpreter window of Cadence Virtuoso. And I'm going to open the library manager. I hope I did. Yeah. And one of the library on the left is called XMODEL_prims, which contains all the XMODEL primitives. So you can basically see what kind of primitives we have. And you can also browse them based on their categories, which I explained. And each of the primitives has the online documentation. Oops, sorry. That describe what each of the primitive does and what kind of parameter they support. Okay. Now, the UCIe library has all those models that I'm going to show today. And the PLL top is the top level schematic of the phase lock loop. So here's a schematic that I described that has the PFD, charge pump, and the VCO that I described with this inline primitive, which contains Verilog code for mapping the control code and scaling the VCO gain as necessary. And lastly, this frequency divider, which is described in the source format. Okay. Now, the reason I popped up this Cadence virtual environments is to show what's called test bench view. So here, what you see for the PLL top cell, in addition to the schematic view and the symbol view, which are the typical view you have for each of the cells, you have a set of views whose names start with TB_. So they're all test benches. And this is what we call test bench view, which describes the settings or maybe the parameters for running certain simulation for that cell. For example, this TB_check lock is a transient simulation that makes sure that PLL locks starting from some arbitrary state. Okay. And you can specify what is the dot that you want to simulate. How do you define the test bench around it? This particular example describes test bench in a source code format, feeding the stimulus and dumping the waveform, also measuring the frequency and phase of the clocks. And the nice thing about this is that once this is all set, to run the simulation, you just have to press this button right here. So all those settings and configuration are encapsulated in one single view. And for running different kinds of simulation for the same dot, you can just pick and choose a test bench you want to run and press this button. Okay, so that's a good way of documenting the test benches you have to run for given cells, and also easy to pass on that information to somebody else. Okay, here what I just did is, I ran a check lock simulation. Okay, not sure what happened there. Okay. What is showing is the transient of the frequency of the output clock of this PLL. We start at 8 gig, but after time it converts to the desired 16 gig frequency. And the phase of the clock also takes time to settle. The frequency first has to settle, and then the frequency. And at certain point, the lock detector decides that it has reached a certain lock and asserts a lock signal. Okay, let's see what you have here. And initially, the input and output of the PLL are not related. They're just completely arbitrary. But once the PLL has reached a lock, then the output clock will contain 16 times higher frequency than the input clock. and the rising edge of the two clock will be aligned. You know, maybe not perfectly, but yeah. Okay. So this way you can run the simulation of these different test bench one by one. Okay. And I'll just flip through the results you can get by running this simulation. For example, you can run a jitter simulation or phase noise simulation. Although I didn't explain, each of the component may have noise parameters, like the frequency to volt, frequency to clock primitive has a phase noise parameter that describe different kinds of phase noise. And those will result in a finite jitter histogram. Also the phase noise. Okay. And you could be also interested in the bandwidth of the PLL, especially that because we wanted to have a constant bandwidth across the different multiplication factor. So one test bench called measure JTran will measure the jitter transfer function of the PLL by literally feeding a sinusoidal jitter to the input clock and see how much sinusoidal jitter we'll get at the output, and to take the ratio between their amplitude at different SJ frequencies. Okay, so here you can see that we do achieve a natural frequency around 20 megahertz, which is what we intended, and this is the result at n equal to 8. So the DC gain of the jitter transfer function is at 8, which corresponds to 18 dB. Of course, we like to verify this is true for all multiplication factors. So there's another test bench called measure TFAC, which measures the same jitter transfer function in an alternate way. So there's a test bench using a primitive called probe AC. I have another example describing its usage, so I'll do it there. But it can plot the jitter transfer function just like in the other test bench, and it verifies that across all n values, the PLL achieves the same bandwidth at, well, I should say natural frequency at 20 megahertz. Well, because the bandwidth is actually around here when, you know, the 3 dB below. And only thing that changes is the DC gain, which is equal to the n. So that's the PLL. Now, I'm going to go to the next block, which is a duty cycle corrector. And there are various ways to correct the duty cycle of the input clock. But the one way that I'm showing here is using a feedback loop. So you monitor the duty cycle of the output clock. If it's not 50%, you make adjustment so that it becomes 50%. So this DCC requires two components. One is the duty cycle adjuster. The other is the charge point filter, which makes the adjustment. So how do we build the duty cycle adjuster? So again, we like to change the duty cycle of input when we propagate the clock to the output. The way we do it is we first turn the input clock, which has a digital form, into an analog form that has finite rise time and fall time. And then we convert it back into a digital output by slicing it at an adjustable reference frequency, reference voltage. So you can see that as we move this level of VC up and down, the duty cycle of the output clock will change. Okay. Now, this is the model of this duty cycle adjuster. First, it has this slew generator that do this first conversion, and then we have a slice primitive that will do the second conversion. This limit primitive is to make sure that VC doesn't get too high or too low, because in that case, you're not going to get any clock at the output, which is actually a disaster. So how do you do the slew generator? It's basically a charge pump that turns on either the up current or the down current that charges or discharges a capacitor. And when you do, you get a linear slope at the output voltage. Of course, we don't want the integration to happen forever. So there is another primitive called V-limit that will limit the maximum voltage and the minimum voltage. So when the input comes in, let's say high value comes in, it will turn on the up current, charge the capacitor, generating the increasing linear ramp over here. And when it reaches the maximum, this V-limit primitive will keep the voltage there. And then when the low comes in, the decreasing ramp happens first, and then reaches the minimum, and it stops there. Okay. Now, one requirement is we like this rise time and fall time to take the fixed portion of the period. And remember, our clock frequency is going to vary over a wide range from 2 gigahertz to 16 gigahertz. So what we need to do is to scale this charge pump current proportional to the input clock frequency, so that the rise time fall time will take this fixed portion of the clock period. Well, one way of doing that, you take the control code again and adjust the charge pump current over here. Okay, that's probably the implementation friendly way. The one way we have done in this model is we pretended that we have a way of measuring the frequency of the clock and then scale the charge pump current proportionally. Okay, here's a simple test bench. So you can also build test bench in this schematic form using the XMODEL primitives. For example, this clock gen primitive feeds a clock into this DCC and is a piecewise linear generator, drives a gradually changing control voltage. And then you observe the output using either a waveform by dumping its waveform or measuring its duty cycle, see if the duty cycle really changes. Here's the result for the input. This is the output of the slew generator having a finite input-output slope. And as the control voltage gradually increases, the duty cycle of the output clock changes because you're slicing at different levels. And you can also confirm that results using the output of the clock to duty primitive. Okay, now we need a charge pump. And what the charge pump does, if the output of the duty cycle is not 50%, then it will have more up period, longer up period than down period, or maybe vice versa. And that will steer the output voltage either to the higher value or to the lower value so that you can correct the duty cycle of the output clock. Again, we like to keep the loop bandwidth of the DCC not, in this case, not constant, because in this case, the input frequency, the frequency of the input clock is changing. So we like the loop bandwidth of the DCC to scale with that input frequency. And turns out to do so, you have to scale the charge pump current proportionally with the input frequency. So we use the same technique that I showed before that will measure the frequency of the input clock, scale the charge pump current using these primitives. Of course, you can do this again by taking the N value from the PLL and then scaling the charge pump accordingly. Just like PLL, this DCC also needs a lock detector. So here's pretty much the same lock detector that observes the duty cycle of the output clock for a certain period. If it stays within the 5% of the final value for 128 cycles, we say, oh, it's locked. And okay, here's again, we also have a set of, let's see, we have a set of test benches defined for this duty cycle corrector model. And here's the model that I just described. And you can run various simulations just by clicking these test bench views. Okay. Oh, I didn't. Ooh. Hopefully it will finish soon. By the way, if you have any questions, just type your questions into a Q&A window, and I'll answer them whenever I have a break. I thought I pre-configured it to Anyway, so I'll just plot. So what you see here is the transients of the control voltage for different operating frequency. And also you see the transient of the control voltage, which is controlling the duty cycle adjuster that adjusts the duty cycle. Okay. And you see a different rates of change because we designed our DCC so that it will have a bandwidth which is proportional to the input frequency. So as the frequency increases, it will have the faster transient, which is optimal for a given frequency. Okay. Okay. For the DCC, we can also measure the DC transfer function, such as the duty cycle of the input clock versus the duty cycle of the output clock. This is typically done using DC analysis, for example, in SPICE. But Verilog is a time domain simulator, so you cannot do a DC analysis directly. So we have a primitive called probe DC, which can emulate that process. So what this one does, it will generate an input stimulus that will gradually change over time. And it will do it in a fashion that's slow enough so that the input can be regarded as DC. Then at the same time, we'll measure the response of your circuit while making that change, and we'll collect all the input and output values and build a table. And after that, we can build a plot, show a plot like this, which shows the DC transfer function between the input and output. For this DC's case, this looks very boring because for all ranges of the input duty cycle, we're just getting the output duty cycle of 50%. Yeah, I said boring, but this is a correct response because this is what we want for a DCC. Similar fashion, we can also do an AC analysis, measuring the frequency domain transfer function of the circuit using another primitive called probe AC. So this one will generate a stimulus, which is the sinusoidal signal that will excite the circuit at different frequency with a small amplitude sinusoid. Then also it will measure the output sinusoid, see its amplitude and phase, and collect the transfer function information. And with this, you can plot the AC transfer function between the input duty cycle and the output duty cycle and check whether your DCC has the correct bandwidth. So this DCC has a transfer function of a high-pass filter because if there's any low-frequency change in the input duty cycle, our DCC is supposed to reject it, right? But if the duty cycle changes too fast, then it cannot correct it, and all the change will show up at the output. So that's high pass. And the cutoff frequency is determined by the loop bandwidth of the DCC. And as you can see that as the input clock frequency increases, the bandwidth also scales proportionally. So this is working as we intended.